In this video, we're going to be taking a look at moments. The objectives for today are looking at what is a moment, taking a look at some additional equilibrium equations. If you remember, we talked a little bit about static equilibrium in the last video with the sum of the forces in x equals 0 and the sum of the forces in y equals 0. So we're going to add to that today with moments. And then we're going to take a look at a sample problem, some different types of supports that we're going to be using for some of our calculations, and then finally we'll get into some beam equations. We'll get some practice with that. So a moment is very simply the tendency for an object to want to rotate about a point. So say you have you're holding a shovel out in your hand and somebody places a bunch of dirt on the end of that shovel. What's going to happen is the shovel is going to want to go down towards the ground. It's going to rotate towards your body because of the added weight. And so therefore, with the added load, you as the user then applies more force to keep the shovel up in the air. So essentially what happened there was we had a moment that was created by the weight of the dirt. We have reaction force, or U, trying to add additional force so that the shovel doesn't move, and the two moments countered each other and balanced out. Therefore, the shovel is balanced in the air. So basically, we're looking at a rotational force. It's the same thing as a torque, but we'll refer to it as moments moving forward. So you can see the equations down here. A moment is equal a force times a perpendicular distance. Now that's key right there to make sure that we're looking at a perpendicular distance. And then finally, in our equilibrium equations, we're going to add the sum of the moments equals 0. We'll also be using the static equilibrium equations from the last lesson, sum of the forces in x equals 0 and the sum of the forces in y equals 0. So let's look at a basic concept of how this works. So here we have a very familiar little drawing, this little setup here. We've got Mary and Johnny both on a seesaw, and we happen to know Johnny's weight at 125 pounds. We do not know Mary's weight, so we're going to have to work that out. But Mary and Johnny figured out that if they stood at, if we put Mary at 6 feet out on the seesaw, but Johnny was only at 4 feet, we figured out that the seesaw would stay level. So they're able to use the seesaw as long as they're in the appropriate distances. Okay, so we're going to take a look at this a little bit further. Here you can see we have Johnny, and Johnny standing at this 4 feet is going to cause our seesaw here, he's going to cause a moment. So if Mary were not standing on this side, we all know that Johnny would travel in this direction until the seesaw hit the ground, right? And so essentially, Johnny creates a moment on, we're going to call it one side of the seesaw, about the point, or about this fulcrum here in which the seesaw pivots around. And the same thing is true of Mary over here. So Mary is going to create a moment in this direction. Okay, so you can see over here that we define what is positive and what is negative, and by the direction that it is going here. So we have clockwise. Johnny would be creating a clockwise moment, so we would refer to that as a negative moment. And then counterclockwise would be a positive moment, as you can see that Mary is causing right there. So using our equations up here, we've got a moment is equal to a force times a perpendicular distance. We know that Johnny is creating a moment, and we know that Mary's creating a moment, and we also know that this beam is not moving, right? The seesaw is perfectly balanced with the locations in which they're standing at. So what that's telling us is that the sum of the moments is equal to 0. In other words, the moment that is created on this side of the seesaw is equal to the moment that is created on this side. And so they're both creating these moments. Since the moments are equal to each other, they're balancing out, and there is no rotation taking place. So let's look at how this works. So we're going to start here with Johnny. We know that Johnny is 125 pounds, so that's important. And we know that the perpendicular distance, so Johnny's weight would be traveling down, so perpendicular to that would be horizontal, so that 4 feet, so we've got times 4. And we know that that is a negative moment, so we're going to put a negative on that. And we're going to say, sorry about that, we're going to use this equation here, the sum of the moments equals 0. So Johnny's moment is 125 times 4, but it's negative. And we're going to add that to Mary's moment over here. Mary, we don't know her weight, so we're just going to call that FM for some Mary. And we know that she's at 6 feet from the fulcrum, so that's going to be times 6. And then if I add these two together, then according to our equation, they should sum up to 0. All right, so we find out that this is negative 500, and this is 6 FM, okay, equals 0. So we can move the 500 to the other side, equals 6 times the force of Mary, and then divide that by 6. You got the force of Mary equals 83.3 pounds. All right, so we know that Mary equals 83.3 pounds in order to balance Johnny out here. All right, so that's the basic concept of a moment. So the force of Johnny is causing a rotation about a particular point, and if we want to find what that moment is, we just need to know what is the force and what is the perpendicular distance to the point of rotation. In our case, it's the fulcrum right here. So let's take a look at another example here. We're going to apply it to something a little bit more specific to what we're doing in POE here. So here we have a little bridge, all right? So this is just a beam that is spanning a distance. You can see I got my little cliff edge here and some water down there. Maybe it's a creek or a river. But essentially we just have this beam, and you would either walk across the beam or a car would drive across, whatever it is. And over here I have a particular type of support or anchor. We're going to talk about those a little bit, and this particular one is what's called a pin support. And then over here I have what's called a roller support. Okay, and then at some point on the beam, which looks like it's actually 16 feet out, we have this 1,800 pounds of load that's being applied to the beam. So before we kind of jump into figuring this out, we need to talk a little bit more about these pin and roller supports. And so I'm going to jump over to another slide here. Okay, so a pin support is signified by this little triangle, and then it has a like a base, and then you can see that it's anchored to the ground with these little slanted lines here. So that's what we refer to as a pin support. And this is a type of support that's used in making bridges or making different structures. But essentially what this looks like in the real world is here would be my beam, and then here we would have like a metal plate, and then this would be a little bolt that goes through. So what this does is if I were to say put a load right here directly onto, well, anywhere, doesn't matter, but what would happen is the bolt would prevent the beam from moving up and down. So the bolt is going to provide a reaction force going back up. So if you put 1,000 pounds down, it's going to push 1,000 pounds back up, assuming that, you know, whatever it's anchored to can handle that. The same thing is true in the x direction. So if I push this way in x, then the bolt is going to push back this way in x, and those two forces are going to cancel out. And so we're going to get what we call reaction forces in the x direction and in the y direction. Okay, so we have reaction forces that are being provided in x and y. Now the interesting thing with pin support though is, since this is just a bolt, it really just acts like a hinge there, a point of rotation. So this would actually be, if we came over and we picked up the end of the beam, it would go up and down, rotating around that bolt right there. That's just not one of the reaction forces that the pin is capable of doing. So, so in this one, the pin support, we have the reaction forces in X and Y. The next one we're going to look at is called the roller support. And the roller support is exactly what it sounds like. It's basically a roller that the other end of the beam would sit on. So like if we were to say connect this piece right here, and maybe it's the rest of this beam, so this would just continue on down and we would have a roller, right? The roller, if I were to say push down on that, right? So if I provide a force that's going to go down, then the roller is going to push back up. So it's not going to let this move in the Y direction. However, if I put a force in the X direction this way, then it doesn't have any way of stopping that. So if this end down here were not attached to anything, you could just roll this beam right off down into the water. But that's not the case because we have a pin support that'll provide that X reaction if we need it. So the reaction forces for the roller support is going to be in X or Y, meaning that in this case it's going to be in the Y direction, the reaction force, because the beam is horizontal. But if, for say, we were to have this mounted to the wall or something like that, to where the beam would be in a horizontal position, then it would provide a reaction force in X. So most of the time for our equations, it's going to provide its reaction force in Y. So basically what you really need to think about is that this has one reaction force, whereas the pin support has two reaction forces. All right, so we'll look at that. And then the third one here, now we're not going to use this much in POE, but is what's called the cantilever support. And so if you think about this, an example of this might be like a deck or something that's hanging off the side of a building. There doesn't necessarily have a support out here, so maybe you've seen like a patio or something that just kind of sticks out the side of the building. Maybe it has a little rail or something up here so people don't fall off. But the cantilever support provides three reaction forces, and you can probably guess what those are at this point. So it has three reactions. It's going to have reactions in the X or the Y direction, in the X direction, and it's going to have reactions in moments. So it'll have a moment reaction as well. So this one's kind of fixed as well. But so we have one reaction force with the roller, two with the pin, and three with the cantilever. We probably won't really deal with cantilevers much in Principles of Engineering. We'll mostly deal with pins and rollers. So no worries on that. Okay, so the next one we're going to look at then is our beam practice here. So I've had people then ask me, okay, well, if that's the case, why do I ever need a roller here? If we got a pin and we got a bridge, I mean, don't we really want to lock this thing in and make it so that it doesn't, you know, move around on us, right? So what I did was I swapped that out and I put two pins in here. Okay, so if I did that, we all know that when we put this 1,800 pounds on the beam, right, we're going to put what's going to happen to the beam? Well, the beam is going to want to bend, right? So we're going to exaggerate this a little bit. But let's say that's my beam, and now we got 1,800 pounds, so now the beam bends. Well, if this has a reaction in X, that means that this pin support is, let me go back to the brush. This pin support is pulling this way, right? And then this pin support is pulling this way. So now all of a sudden, inside the beam, you have these forces that are pulling on each other, and basically what will happen over time is we get a crack here, we get a crack here, and the beam will start to pull itself apart because of these internal stresses created by the bending. So we have to be able to allow the beam to move. And not only that, we have obviously the bending that takes place from applying a load, but we also have bending that are expansion and contraction due to heat or due to the temperature. So this beam needs to be able to move around a little bit so that we don't create internal stresses inside the beam. So that's why we would go with a pin support over here. It provides us our X and our Y, and then the roller over here provides us with our Y support, and we are good to go. So we're going to go ahead and we're going to solve this equation. We're going to figure out how much exactly this pin is holding and how much this roller is holding based on 1,800 pounds at 16 feet. Okay, so we're going to make a couple assumptions here. Number one, we're going to call our pin support our fulcrum. This is going to be the point of rotation. We know that this 1,800 is causing a, is it positive or is it negative? Okay, do you remember? Positive is going to be a counterclockwise, and negative is going to be a clockwise. So this is actually creating a negative moment about the pin support here. Okay, and then we know that the roller over here is really what's stopping it from the beam from moving. So the roller is going to provide that positive moment to counter the 1,800 here. So the first thing we're going to do is we're going to redraw this setup into a free body diagram. We're going to have our pin support here. We're going to have our roller support here. And then we're going to put in the forces. So I know that the pin support has a reaction in X and in Y. And then the roller has one in Y. Okay, and then we'll just put a line to connect these two here. There, and we'll make this green. Why not? Okay, and then we also have the we already know we have an 1,800 pound force at 16 feet according to the drawing here. Okay, so now I'm going to go ahead and draw in some arrows here. These are the directions that I think the reaction forces are going to have to go. You know, I don't know these for sure, but I'm going to just assume that they're positive at this point. And if it comes out negative, then that means I know my arrow direction is incorrect. Okay, so we're going to start out, let's label these things. Let's call that point A. Let's call this point B. And now we can go ahead and get started with using our equation here. The sum of the moments equals 0, knowing that a moment is a force times a perpendicular distance. We also know that point A is the point of rotation. So the first moment that that's being caused if we go out the beam would be this 1,800 pounds. So this 1,800 pounds is causing, you know, this direction here. So that is going to be a negative moment. So we're going to take the moment that's created, negative 1,800 times the distance, 16 feet, and we're going to add it to any other moments that we have. So let's go further out the beam. Here we have a reaction force at B that is opposing that. So we're going to have the reaction force at B in the Y direction times, what is its distance all the way to the fulcrum? Well, 16 plus 8 should be 24 feet. Okay, and then no other moments are being created. So I'm going to set that equal to 0. So some people would ask then, okay, well, what about these two here? Well, we could include those into our equation right here, but the thing you have to understand is, what is the distance? So are they actually creating a moment? If I'm looking at this reaction force here, so we'll call that the reaction force at A in the Y direction, we can take that and multiply it by its distance to A, which happens to be 0. So therefore it has no moment. It's not causing any rotation. Same thing with this. Its perpendicular distance from A is 0, so it would not have a moment either. So using the pin support helps, or as your rotation, using the pin support as your rotation helps to kind of eliminate some unknowns so that we can focus on the roller support and solving for it over here. So if we were to do that, we would find out that, let's see here, so I have 1,800 times 16. That gives us a really large number, so we have negative 28,800 plus 24 RFBY equals 0. So if we have 28,800 over here, and we have equals 24 RFBY, divide that by 24, we get the reaction force at B in the y direction is 1,200 pounds. That's required to oppose the 1,800. So the reaction force over here is holding 1,200 pounds. All right, so we've got that. We know that if it's going to hold the 1,800 out here, you only have to hold 1,200 out here. So really it's kind of acting like a second-class lever, if you remember that back from Unit 1. All right, so then what do we do about these guys here now that we know this? Well, there's a couple different methods you can do that. I'm going to show you using our static equilibrium equation. So we have the sum of the forces in x equals 0 and the sum of the forces in y equals 0. And I already know that this whole system, right, this whole beam is not moving, right? It's at rest. So that means that not only are the moments in equilibrium like we saw here, but that also means everything in x is in equilibrium and everything in y is in equilibrium. So what that means is if I have 1,800 going down, I have to have a total of 1,800 going up. So here I have, so if I wanted to look at that and use the sum of the forces in y, so the sum of the forces in y equals, I have a negative 1,800, because that's going down in y. I have a positive 1,200, and then I have over here what looks to be a positive, so plus the reaction force at A in the y direction. All of those together equals 0, and we find out that reaction force at A in the y direction is equal to 600. So I have 600 here, so then 1,200 plus 600 is 1,800, so that's balanced out. Now we're looking at the sum of the forces in x. Well, I only have one force in x, and if I only have one force in x, and the sum of the forces of x has to equal 0, then I know that this guy equals 0. There is no force in x with this particular setup. So if you have any questions, please reach out and let me know.